Here are few problems in wave mechanics. See the first problem. Which of the following particles will have the shortest de Broglie wavelength if they have the same kinetic energy? All the four particles are having the same kinetic energy. Among the four, which one has the shortest de Broglie wavelength? That's the question. You know the de Broglie wavelength lambda equal to h by mv. This is expressed in terms of kinetic energy as h divided by 2m into k inside the root. Here k is our kinetic energy, half mv square. If you put lambda equal to h divided by root of 2m into 1 by 2 mv square, then lambda equal to h divided by m square v square inside the root, that is equal to h divided by mv. The original equation we can have. Therefore, we may express the de Broglie wavelength lambda in terms of kinetic energy k, that is h divided by root of 2mk. Lambda equal to h divided by 2m into k. Here k is our kinetic energy. In this problem, they have pointed out that all the particles are having the same kinetic energy. K value is same. Then the affecting factor is mass. Greater the mass, smaller should be the wavelength. Among the four particles, electron, proton, alpha particle and neutron, alpha particle has greater mass. If the value of m is large, the value of lambda is low. Therefore, option C, alpha particle, is correct. Now go to the problem 2. A particle is moving such that its de Broglie wavelength is equal to the diameter of a hydrogen atom. That particle is most likely A or an alpha particle. That means a particle is moving such that its de Broglie wavelength is equal to the diameter of hydrogen atom. That particle is most likely an alpha particle, a neutron, an electron, a proton. Among the four, we have to choose one answer. Read out this question. A particle is moving such that its de Broglie wavelength lambda is equal to the diameter of the hydrogen atom. The diameter of the hydrogen atom is 0.1 nanometer. That particle is most likely, the answer is an electron, because the wavelength of low energy electron is 0.2 nanometer. See here, a particle is moving such that its de Broglie wavelength is equal to, that means the de Broglie wavelength of electron is equal to diameter of the hydrogen atom. Diameter of the hydrogen atom is 0.1 nanometer. If you think about low energy electron, the wavelength of low energy electron is 0.1 nanometer. Here they have given diameter of the hydrogen atom. A particle is moving such that its de Broglie wavelength, that is lambda, is equal to the diameter of hydrogen atom. That means lambda of electron equal to diameter of hydrogen atom. Therefore, the answer is option C, electron. See the third question. Which of the following best explains why the wave nature of macroscopic objects like cricket ball is not observed? We may not observe dual nature as far as the cricket ball is concerned. Now you have to provide the explanation for that. We know the value of lambda. Lambda equal to h divided by mv. The Planck's constant is expressed in terms of 10 power minus 34. If you think about a cricket ball, suppose if may consider the cricket ball in terms of gram. To convert gram into kilogram, we may use 10 power minus 3. Say 500 gram, 400 gram, like that. To convert gram into kilogram, we may use 10 power minus 3. Then velocity is few centimeter per second, velocity of the cricket ball, if it is in motion. To convert velocity in terms of meter, we may use 10 power minus 2. In order to convert centimeter into meter, we may use 10 power minus 2. Therefore, the momentum is expressed in terms of 10 power minus 5. This is 10 power minus 34 divided by 10 power minus 5. This is equal to 10 power minus 29. Such a smaller wavelength is not predictable. Therefore, for this problem, the exact answer is their de Broglie wavelength is too small to detect. Say here, suppose a cricket ball is in motion, even though it is having wave nature, the wavelength associated with the motion of the cricket ball is 10 power minus 29 meter, which is not a predictable one. Therefore, option C is correct. Next, we will go to the fourth problem. If the kinetic energy of a non-relativistic particle is quadrupled, what happens to its de Broglie wavelength? Option A, it becomes 4 times longer. Option B, it becomes twice as long. Option C, it becomes half as long. Option D, it becomes 1/4 as long. We know the formula for de Broglie wavelength in terms of kinetic energy. lambda equal to h divided by 2m into k. Now the kinetic energy is increased to fourfold. Then what about lambda dash, new wavelength, which is equal to h divided by root of 2m into 4k, which is equal to h divided by 2 into 2mk. Lambda dash is equal to h divided by 2mk is our lambda whole divided by 2. You may take this 4 outside as 2. Rest of the things are present as 2m into k inside the root. h divided by 2m into k inside the root is our lambda. Therefore lambda dash is equal to lambda by 2. If the kinetic energy is fourfold, then the wavelength is reduced to lambda by 2, half of the wavelength. Therefore option C is correct. We'll go to the next problem. Problem number 5 we have to discuss. A particle is described by a constant wave function psi of x equal to a over all space. What can be concluded about its physical properties? Option A, definite position and uncertain momentum. Option B, definite momentum is 0 and completely uncertain position. Option C, definite momentum, here non-zero, and definite position. Option B, both position and momentum are uncertain. Now you have to give the explaining for this. Actually, psi of x equal to A represents a plane wave having wave number value k equal to 0. This is delocalized. See that a particle is described by a constant wave function psi of x equal to A over all space. What can be concluded about its physical properties? There are given 4 options: definite position and uncertain momentum, definite momentum within the bracket 0 and completely uncertain position, definite momentum non-zero and definite position. Both position and momentum are uncertain. Here psi of x equal to A means there is equal probability of finding the particle anywhere. It is completely localized. Completely delocalized. Completely delocalized. Here the meaning is the wave number k equal to 0. Suppose wave number k equal to 0, lambda is approaching infinity, then p equal to h by lambda, which is equal to h by infinity equal to 0. From this you may add out the result. Suppose the wave function is constant psi of x equal to A, which represents a plane wave. Therefore, the probability of finding the particle anywhere, it is completely delocalized. The particle is having the probability to occupy any space. At that moment, the wave number value k equal to 0. K equal to 0 means lambda is infinity. Suppose lambda infinity means momentum is 0. Momentum 0 specifies that definite momentum, here 0, and completely uncertain position. See this psi of x equal to A means there is equal probability of finding the particle anywhere. Therefore, uncertainty in position is dominating, whereas the momentum is definite, that is 0. If k equal to 0, automatically the value of lambda equal to infinity, because lambda equal to h by p, p equal to h cross k. If k is 0, then momentum is automatically 0. Suppose momentum is 0, anything by 0 is infinity, lambda is infinity. From this we may conclude that definite 0 momentum and completely uncertain in position, because it is a plane wave. The particle may occupy any point in that particular plane wave. Therefore, the probability of finding the particle is having higher uncertainty. Therefore, the option B is correct. Definite momentum, that is 0, and a completely uncertain position. We will discuss the rest of the things in the next lecture.